as the name implies, is modeling a given set of data with a sine function. And it says at the top, since y equals sine x and cosine x differ only by a phase shift, it's possible to use either sine or cosine when finding models for periodic data. Periodic data is just data that kind of repeats itself over a certain period of time. But it might be necessary to use phase shifts in our calculations to make sure that we can get a model to fit the data. And since the calculator just has sine regression on it, we're going to specifically pick out sine models today that hopefully can model our set of data nicely. That being said, you might wind up finding that it looks cosine-ish, but remember, like it says up at the top, sine and cosine graphs are only different by a phase shift. So just as a quick reminder, what does the graph of sine x look like? We're looking for something today that has this type of shape to it, right? So it's going to go up, come down, and then that's what one completed cycle of the sine curve would look like. So we're going to see hopefully trends in the data that might be able to model something that looks like that. Keep in mind, if I were to shift this graph over a little bit to the left or right, it might start to look kind of cosine-ish, right? But this would continue on in this path over here. So just know that we're going to hopefully see a trend in the data that models this type of path. So go ahead and type your data into list 1 and list 2. I actually don't want you to run any type of regression yet, but just have it stored there. We're going to come back to that in just a little bit. But the first thing you might want to do is actually just plot the data over here. And if you do that kind of quickly, we've got 123.8, just kind of a rough sketch so you can see what this looks like here. 2, 27.7, 3 is 37.9, just real rough here. It doesn't have to be anything too specific. Try your best to be accurate. All right, so 7 is at 74. That looks like it's actually the peak. Okay, this is actually the highest y value on our scale, so that's going to be of importance to us. Then we're talking about Chicago's monthly average temperatures here. So we know that during the summer months, it's going to go up, and then it's going to, in the winter months, go back down. So 8, we're at 72.4, which would be, let's say right about here. And then 64.6, 52.5, 40.3, and the last one at 27.7. Okay, hopefully I did an okay job plotting those points. All right, we haven't done a lot of scatter plots by hand yet, but now that we have this model, I'm going to challenge us in both examples today, and there are only 2 examples, to find the model using this data. And we're going to first try to find the model by hand. So you'll notice that in part C, it says use the graphing calculator and do a sine regression, but this actually is a great review of what we've done so far this year with talking about equations of sinusoidal functions. So what we're going to do is we are going to have to think about what do these values A, B, C, and D represent. And I'll start with the value D in this scenario. So D is the midline. And to find the midline, which is this line that the sine function wraps around, right? I drew the parent function that wraps around the x-axis, but if there's any kind of vertical shift, that's what the value D tells us. It's actually just the average of the highest and lowest points on the graph. That's going to be the line that this sine graph is wrapping around. So the lowest y value is at 23.8. So if we find the average of those, if we do 74 plus 23.8 and then divide that by 2, the value of D in this example should be approximately 48.9. So if I go to 48.9 on the graph and maybe just make a little bit of a dotted line here at 48.9, that's the line that this periodic sine function would wrap around. So we have that drawn in there. If we continue on from there, maybe the next easiest thing to find is the amplitude. And then if we find the amplitude, do you need me to go? All right, sorry for the pause there, guys. To find the amplitude, it's going to be the height above and below that midline. So actually to find the value A, which is the amplitude, you could pretty easily calculate that by doing 74, the highest point, minus the midline. So 74 minus the 48.9. In this case, gives you an amplitude of 25.1. That should also represent the distance from the midline down to the lowest point on the graph. Okay, so we got the value of A, we've got the value of D. Moving on to the value of C. Okay, so C represents what's called the phase shift. And the phase shift is how far to the right or the left we've shifted. So if you notice the original parent function, the original parent starts right on that midline. And you'll notice in our graph, this function hits the midline at an x value of 4. So what we have to do for the phase shift we have to shift to the right 4. And we move to the right 4, that's going to indicate that C in this example should have a value of -4. Remember that when you shift left and right for functions, we're going to have to say that it's -4 for the value of C in order to get that shift to the right. All right, moving on to the value of B. B is the last thing that we're going to calculate. B is the frequency. And what we're actually going to use to find the frequency is this concept that we've talked about with period. Period in general is 2 pi divided by the frequency. If you remember anything about the period is how often one full cycle of this graph is completed. Now, it may not appear that way, but I think we're seeing one full cycle of the curve within this 12-month time frame. And if you look at this right here, if you think about taking this sine parent function and then kind of just shifting it to the left a little bit, you would get, like this is one full sine cycle as well. It looks more like upside down cosine to me, but it could be representative of a full sine cycle. So what we're going to do in this scenario is say that the period for this specific case is equal to 12. Okay, we have one completed cycle by the time we get through 12 months, which makes sense, right, through a year. So if you solve this for B, you're going to wind up getting that B is 2 pi over 12, which would reduce to pi over 6. So if we're solving this right here, we wind up getting B equals pi over 6. And then after we get all those values, we're going to go ahead and just plug them into the appropriate spots in our standard form up here. So the equation for our sinusoidal model that models this data. Oh, my daughter needs help. I'll be there in 1 second, Els. So we've got y equals 25.1. Then we get sine of the value of B, which is pi over 6, times x minus 4. And then at the end, the vertical shift plus 48.9. Okay, go ahead and if you haven't already, type that data in and see if you can get the sine regression model. And we're going to compare and see how close we came to getting a model that actually works well here. Okay, I'm back. Sorry about that, guys. Here we go. So we got stat edit. I have my data already typed in. This is actually the data for what we're going to get to on the back in just a moment. But if I go to do a sinusoidal regression, maybe you've already found it. Stat calc. It's option C. Now, something that you might have had a question about while I was gone there is what does it mean by iterations? The iterations are the number of times that the regression model sort of runs through its process to calculate the sine model of best fit. And the default on the calculator is 3, and that really should be fine for us. The max number of iterations the calculator will do is 16. And I guess that would ensure the most accurate model, the more times it kind of runs through this process here of calculating the regression. However, it does take more time the more iterations that you have. So go ahead and just leave it at 3. I'm going to do L1 and L2 here. And then for period, if we know the period, you can type it in. And I realize that we've already calculated that. But if we didn't do all the work by hand in advance, we wouldn't have known the period of the graph most likely. So we can just leave that kind of blank for now. The calculator will fill it in for us. And the last thing is I'm going to store this equation in y1. Remember to do that, you hit vars over to y bars, hit enter for function, and then enter for y1. Go ahead and hit calculate. And there's our sign model of best fit. So let's go ahead and write down that equation here. It says round to the nearest 10th. So I got y equals 25.2, which was pretty close to our amplitude of 25.1, sine of, and then the value of b to the 10th place is 0.5, and then c is -2 plus 48.7. So our midline that we had at 48.9, really, really close to what the midline is here. If you're looking at the frequency and you're saying that doesn't really look like pi over 6 to me, well, pi divided by 6 is about 0.5, right? 3.14 divided by 6. So that seems like it's making sense. Well, why is this a -2 though and not a -4? It's because here the frequency is factored out. So if you factor out 0.5 from this expression, it's going to read x -4, which then really, really closely matches what I have here. Now remember, we have our regression equation stored in y1. One of the most important things is, I mean, look at this value that I have for my frequency here. That is definitely in radians. So you have to make sure that when you go to graph this, that you have to be in radian mode, which my calculator is. Maybe double check that before you go ahead and take a look at the graph. But if I go to y equals right now, my regression equation stored in there. My stat plot is already set up. So it should be on list 1, list 2 for the scatter plot here. If you hit zoom 9, that's pretty close to the model that we just graphed by hand. And then you can see how great our sign model that the calculator came up with here fits our data in this case. And the one that we came up with, using our knowledge of what each of those coefficients represent, I think is really, really nice model too. So the last thing I want us to do in part D here is go ahead and predict the average temperature for June using both models. So we'll use the one the calculator came up with. We'll use the one that we have in our example as well. Make sure that if you're doing this, again, stay in radian mode. The sine of pi over 6 times something is only going to make sense if the calculator is in radian mode. So using our model, we have to enter for June, that would be month 6. So you would get y equals 25.1 sine of pi over 6 times 6 minus 4 in parentheses, which I realize is 2. If you want to go ahead and just write a 2 there, plus 48.9. And if you type that into the home screen, we're going to get 25.1 sine of pi over 6 times, like I said, we could just make that a 2 in there, plus 48.9. I got 70.64 for the temperature here. So using our model, we should get that the average temperature in June is 70.64, which the actual average temperature in our data was 68.9, so that's pretty close. And then if we use the calculator model and we plug in 6 for x, so the calc would be y equals 25.2 sine of 0.5 times 6 minus 2 plus 48.7. You guys can type that in quick and see and double check that you get the same number as me. Now I got that the average high temp is 69.91 degrees. So that's even a little bit closer to what the actual data point suggests, that in month 6 that the average temperature was 68.9. So something we haven't really discussed a lot is when we use our models to make predictions, we shouldn't expect them to be perfect. They should be close if we have a model that kind of makes sense and looks like it's grouped nicely with the data. But at the end of the day, there's going to be a little bit of an error involved. And in fact, analyzing error, which in statistics is known as residuals, analyzing that error sometimes can help you to determine whether or not you have a model that makes sense. Okay, so that would be something you might talk about in AP Stats next year. All right, I want you to go ahead and try the one on the back on your own. So we talked about the logic that we used to find the values of A, B, C, and D on the front. Notice how on the back, I actually want you to make one quick fix here though. For 335, For some reason, that was a quick typo. It should be day 338. These are days within a year, and then the number of hours of daylight that Chicago has. So we're really into Chicago today. I've never been to Chicago, but I'd like to go because deep dish pizza sounds really good. So I want you to give this one a try. See what you can come up with on your own to find the values of A, B, C, and D by hand. The one thing I think that's a little bit tougher in this example is C, because it was a little bit easier in our case to determine the phase shift because we had a point right on that midline, right? The Y value of 48.9 corresponded with a shift over 4 to the right. In this example, it's a little bit tougher to determine that. So make your best estimate, make your best guess, and that's fine because that's all this really is an estimate. And then see how close you are when you do it on the calculator in part B. And then go ahead and try part C too, making a prediction based on the models. I'm going to go ahead and start showing my answers to this part. So again, I'd recommend just hitting pause real quick, give this last page a try on your own, and then see if you can get something that's pretty close. Okay. Taking a look at this back page here. So looking at the high and low values that are Y values in our data set, if you find the average of those values, add them up, divide by 2, that's going to be your midline, so that one shouldn't be too tough of a calculation. If we take a look at the phase shift is, I said it was right 85. Now, if you pick something, I hope you pick something somewhat close to that. You'll notice that it has to happen sometime between 60 and 91. Okay, that phase shift. And 12.72 is pretty close. It's definitely above the midline for a Y value, but I tried to pick something relatively close to 91 days. And I kind of settled on 85 days later would be approximately when the height would be 12.185. Okay, so that's how I made that decision. I think that's probably the toughest one to come up with, but once you come up with some of this other info, like you can find the amplitude. The amplitude would be the max height minus the midline. So in that case, that would be 2.985. And since we're looking at this over the span of 365 days in a year, we get that 2 pi divided by the frequency. B would equal 365. So then here's my calculation for B. And putting all of that together, here's the equation that we can come up with using our values for A, B, C, and D. Okay. So then it says determine the sinusoidal regression model to the nearest hundredth. On the front, we only went to the 10th place. Here's what it is to the hundredths. This is what the calculator gives you if you do the stat calc, and then it's option C, like we saw. And then I think what's interesting about part C, it says use both of your models to predict the period of time during which Chicago gets at least 12 hours of daylight. So 12 hours of daylight is a Y value. So we're plugging in 12 for Y here, and we have to solve for X. Well, the easiest way to do that is definitely using a graphical technique. So you're going to plug your equation into Y equals, okay, I would store the regression equation somewhere maybe, and then in Y2 type in 12 and see where those things intersect. Here are the results that I got for that. I'm going to show you a couple things on the calculator though. So according to our model, here's what you should get. That you'll see that the graph is above 12 over the interval from 81.4 days to 271.1 days of within a year's time frame. Now, when I say here's what the calculator gave me, I'll tell you that these calculated values, those intersection points when the graph is above 12 hours, that this was the model stored in Y1 when I do the sine regression. This was the rounded version from the calculator. So if I take this rounded answer to the hundredths place, notice how different the full sine regression model and this rounded version are, especially at the larger end, right? I mean, it's the difference of day 225 versus day 268. That's like a whole nother month later. So in terms of accuracy, I think we really have to be cautious about rounding our model. It did say to round to the hundredths place up there, but notice how drastically different these values are than what the calculator suggested, and even what our model suggested. These are much closer in relationship than these two answers here. So just because I thought it was interesting to look at quick, I did enter the data into list 3 and list 4. So when you go to do your sine regression, if you're going to follow the same process as me, you would have to change L1 and L2 to L3 and L4. I'm going to store the regression equation in Y1. Okay. Calculate that. And the only thing I'll also have to do a little bit differently here is I do have to go into my stat plot, and I have to make sure that I'm graphing the data in L3 from L3 and L4 and not from L1 and L2. So I'm just changing these things so that we're not modeling the data from the front page. We're doing the back. And if I hit zoom 9, okay, we can see how close the sine regression fits this set of data. But I think you'll be interested to see what happens if I type in the data or the equation rounded to the hundredths place, right? I mean, look at all those decimal points that go out when you just store the equation in Y1. If you go and just round to the hundredths and do 2.99 sine of 0.02x minus the 1.32 plus 12.14. Oops, that's not going to look right. All right, assuming I've typed that incorrectly there. If I hit zoom 9 now, it does a decent job in the beginning, but look how it kind of falls off over here, right? It reaches its peak way too early. So I think you really have to be a little bit cautious when you do regression in general. You know, how far out should we round? Well, we're going to follow the directions for now. This one said to the hundredths place, but notice how rounding to the hundredths and then using this as a model to make predictions later on wasn't the most reliable situation. Okay, storing the equation in Y1, much more reliable. And our model that we came up with, it actually wasn't bad. I mean, this is what it really should be the closest to right here. But our model wasn't really too far off of that. So just keep that in mind. Be cautious when you're using statistical models and with rounding specifically. It doesn't seem like it would make that big of a difference. But in the grand scheme of things, it actually does. Okay. That's it for sinusoidal modeling and regression. You'll notice that the homework for this day has a little bit of practice with some old trig stuff, which is not bad to kind of get back in the mindset of for our final trig review that we have coming up. And then you'll see that tomorrow's lesson is just a little bit more practice where you have to choose what you think is the best model. Okay. All right. Let me know if you have any questions. We'll talk to you guys soon.